Hello, curious minds. Welcome back to F4ctify, your go-to destination for unraveling the wonders of our world. Today we're embarking on an adventure into the celestial blue, solving a mystery that has piqued human curiosity for ages. Why is the sky blue? To answer this, we need to dive into the world of light and its interaction with our atmosphere. This brings us to a phenomenon known as Rayleigh scattering. Picture this. As sunlight, a mixture of many colors, makes its way into our atmosphere, it meets molecules and tiny particles. These encounters cause the light to scatter in different directions. But here's the fascinating part. Blue light, with its shorter, smaller waves, scatters more than other colors. And it is this scattering extravaganza that paints our sky in its everyday blue. This scattering effect is what bathes our sky in that beautiful blue hue. Now let's break down sunlight. Imagine sunlight as a vibrant rainbow painted across the sky, an orchestra of colors each playing a different note. These colors, from the deep reds to the cool violets, represent a spectrum of wavelengths. Blue light dances on the shorter end of this spectrum, moving in quick, tight waves. On the other end, you'll find red light striding in long, leisurely waves. This difference in wavelength is key to why our sky often dresses in blue. As sunlight, this mix of colors, enters Earth's atmosphere, it meets a crowd of molecules and tiny particles. Due to its shorter, faster waves, blue light is more prone to bouncing off these particles in all directions, a process known as scattering. This scattering paints our daytime sky in a wash of blue. But what about those stunning sunrises and sunsets, where the sky blushes in hues of red, orange, and pink? Well, atmospheric conditions have a starring role here. During sunrise and sunset, sunlight embarks on a longer journey through the atmosphere. This marathon run scatters away most of the blue and green light, leaving the stage to the warm tones of red and orange. This longer path scatters more of the shorter wavelengths, allowing the warm tones of red and orange to dominate the sky, creating those breathtaking sunrise and sunset moments. Another player in the game is the Tyndall effect. This phenomenon, named after the 19th century physicist John Tyndall, is all about the scattering of light. When light meets the gases and particles in our atmosphere, it scatters in all directions. This scattering is particularly pronounced for shorter wavelengths, and remember, blue light falls into this category. So when you gaze at a cloud of smoke or a misty horizon and notice a bluish glow, you're witnessing the Tyndall effect in action. But let's not forget about the role of our own perception. We humans are pretty well tuned to blue light. Our eyes, particularly the cells in our retinas called cones, are more sensitive to this shorter wavelength light. As a result, the scattered blue light stands out more prominently in our vision. That's why during the day, the sky appears predominantly blue to our eyes. There you have it, the quick and fascinating explanation of why the sky is blue. We've journeyed through the intriguing dance of Rayleigh scattering, explored the colorful composition of sunlight, witnessed how atmospheric conditions impact our sky's hues, delved into the Tyndall effect, and even discovered the role our own vision plays in perceiving the sky's color. Thank you for joining F4ctify on this journey into the science of our sky. Until next time, keep looking up